Good afternoon. I'm Deborah Ashby. I'm the president of the Royal Statistical Society, and it's my pleasure to chair this discussion meeting, which is the second discussion meeting of the current session. So a very warm welcome to all fellows, all visitors to this meeting. Some of you are well familiar with this format, others it may be your first exposure, in which case I hope you enjoy it. Now, the tradition is that fellows and visitors are invited to contribute to the discussion of the paper, so please, if you've got something to say, feel free, but there's a format for doing it, which I'll explain in just a moment. I need to inform you that the meeting is going to be filmed and posted on YouTube afterwards, along with the slides. If anybody objects, could you let me or one of the RSS staff know so that the contribution can either be made audio only or edited out? Now, what we're going to do, we've got two papers, which I'll introduce slightly more specifically in a moment, and they're going to talk for about 25 minutes each. We then have, and it's a tradition that we call it the proposer of the vote of thanks and the seconder, and they've got 10 minutes each. After that, I will be opening it out for discussion, and the tradition is each discussant has no more than 5 minutes, and you would be expected to put in a written version afterwards, but you don't have to have that with you at the moment. So if you think of something you want to say during it, then you'll get your opportunity. We've also got several written contributions that, if time permits, then Paul Smith will read some of them out, but we will give precedence to the people who are here if we get short on time. So I hope that's clear. It looks like an absolutely fascinating meeting, and so with really no more ado, what I'm going to do is to introduce the first paper, which is called Knowing the Signs, a Direct and Generalizable Motivation of Two-Sided Tests, which Ken Rice is going to go and present. Now, what I need to just to point out is that we do have written versions of both papers, and so if people want them, I don't quite know the best way that the judges could take some down or pass them down, but if you haven't already printed it off and read it, but you'd like them, they are being passed around, so that's what's going on there. So, while that's happening, perhaps I can ask Ken Rice to come up and to present his paper. And he's come from Washington, Seattle, so particularly warm welcome.
Thank you. While you're getting the copies of the paper, then I'll just briefly summarize the talk. It's about taking testing from being a sort of yes or no, stop or go decision to being one that's just slightly more nuanced. As I explained to my American colleagues where I've lived for quite a long time now, you can either turn left or you turn right on British roads, or mill around aimlessly in the middle in a way that they don't really understand with roundabouts. So that's where we're going with this talk. We're going to develop decision theory, which will motivate significance tests from a Bayesian point of view, but also could be used in other paradigms. And so this work is somewhat practically motivated, as well as having a philosophical bent. So what do we want from testing? Testing is a hugely controversial area, as I'm sure you're all well aware, with replication crises and similar problems. But how would we like testing to work, and particularly work better? And I'm going to be thinking about this for a real valued parameter theta, about which we want to make some testing-based decision. I do this a lot in high-throughput genetics. I have a lot of real valued parameters, and I want to make decisions about them, saying whether some genetic variant is or is not associated with the disease endpoint. Based on this, then some criteria that would be good and bad for testing. Things I want to avoid are having, taking a Bayesian point of view, having a prior distribution which has got a spike at exactly 0, saying, for example, in my world, that there's exactly no association between a genetic variant and a disease outcome. We don't believe that, typically. It might be close to 0, but it's never exactly 0, and therefore I don't want to conclude that the truth theta is some exactly null value. That's not how the science works in practice. It's not a conclusion that it makes sense to have in the statistical setup that describes it. We can live with one-dimensional parameters. We've got, in my case, hundreds of millions of them, and so dealing with them one at a time is perhaps not completely optimal, but perfectly sensible place, and again, how the world works in that field. Sure, we'll have parametric models. You can actually generalize all of everything I'm going to say today to slightly less parametric settings, though I won't do that today. And perhaps more controversially, I'm only going to specify the sign of parameter theta. Is it positive? Is it negative? Is as nuanced as we need to be, and that's actually realistic, again, in my world of high-throughput genetics, that all we want to do is to find some interesting signals that we can then follow up in replication, the sort of stuff that Leo's going to talk about in the next talk. But just saying it's positive so we've got something to go after is not much of a conclusion, but it is enough to move the science down the road, and so that's not just sort of mathematical artifice, that's real there. Then it must be simple to explain. I don't need to tell people in this room that statistics can be hard to explain to people, and so we'd like to make it simpler if at all possible. Some measure of optimality so that people don't do poor analyses, that they do the best thing possible with their data. They want to do that, and we want to do that for them, so having that there is reasonable. I'd really like it to be connected to P's because I've already published literally hundreds of millions of them, and I hope that all that works not wrong. It seems to work okay in practice, so some connection to what people do at the moment would be useful. And then, as you may be able to tell by the accent, if it hasn't been obliterated by living in the States, I would prefer that it be Scottish. And why? Because we have a useful lesson to draw from the Scottish legal system, it turns out, which is different from the legal system in other bits of the UK. And in particular, it's got 3 possible verdicts. All the Scots folks in the room know this, but for everyone else, then you can be in a Scottish trial where you're tried by some guy in red robes up here. You can be found guilty, you did it. Not guilty, you definitely didn't do it. Or this third thing, not proven. Where you are not found guilty or just not evidence to make a conclusion either way, essentially. There's an old Scots lawyer's joke that not proven means not guilty and don't do it again. So it's interpreted that way. And that decision's not really there. We can't say, well, we just don't know. And for lots of practical situations, of course, then yes, we just don't know if there's a reason to conclude something exciting and positive or something null and unexciting, or just not say anything at all. So how do those verdicts overlap with test-based decisions? Well, for the classical sort of Neyman-Pearson hypothesis testing version of things, you can either accept or reject the null hypothesis, of course, and that's like saying that the defendant is either guilty or not guilty. Fisher's approach to testing is slightly different than significance tests. Everything revolves around doing the test in the same way, but the interpretation is slightly different. Sure, you can reject the null hypothesis or just not say anything at all. And there's not really an accept the null choice in Fisher's setup. You could argue reasonably, I think, that these 2 rows at the bottom, not proven, not guilty, sort of both get rolled into Fisher's no conclusion, Fisher's null result there. And so it would be nice to have a way of saying not proven. It would also be nice to have a measure of optimality, and that's where the decision theory comes in. I'm going to be sort of fully Bayesian here and specify not only a prior and a likelihood, but there's going to be a loss function as well, which we're going to minimize to choose the optimal decision. That's where the optimality comes in. The good news is if we're just deciding whether a parameter is positive or negative, that's the only function of the truth that we care about, whether theta is above or below 0, then there aren't that many loss functions that you can have. And particularly for hypothesis tests, this is the simplest case, so we'll deal with it first. There's only 2 things you can say there. Yes, that theta is above or that it's below, and then you could have some loss depending what the truth is in both of those situations. So you get a 2x2 table, obviously, for the 4 different combinations. Each of those has a value of loss, how bad it is if we do one thing when the truth is either agrees with it or doesn't agree with it, 4 different values of loss there. There's a restriction on loss functions making them proper, which essentially says that you should have the minimum loss when you tell the truth. Telling the truth, when possible, should be the optimal thing to do, and that, it turns out, without loss of generality, is what constrains these losses when you do the right thing, when the truth is positive when you say so, or the truth is negative when you say so, score 0 loss for those. For all the rest of the entries, there's just 2 values, and one happens to be bigger or smaller than the other, and it's only the relative values of loss that matter, so it doesn't matter what their absolute values are, and so this constrains this tells us how to fill in the other two squares on our 2x2 table there with some number that we're going to call alpha, and that's going to turn up to be Darwin error rate in a frequentist setting. Anyway, that's all you need to specify your loss for a hypothesis testing decision. Your Bayes rule in this case would, it's well known, this is not a particularly new result, would say that make the decision to say that the truth is above 0 versus below when the left tail area is small, smaller than that alpha that was encoded in the loss function up there. And that's going to act like a one-sided p-value when you've got large samples, when the prior doesn't really matter that much and everything is coming from the likelihood. But it doesn't have the useful or familiar behavior from two-sided tests that we double the smallest tail that everyone's familiar with when doing hypothesis tests. So it's not quite getting at the same thing that the frequentist version is. We're going to get closer to the frequentist version with a one-sided significance test here, which is going to be more like the Scott's law not proven verdict. And instead of having just decisions that you can be above or below 0, I'm going to have two decisions. One that you can be above, that's the exciting one, then send your results off to nature or science, and then the null decision, which I'll call no decision. Don't include anything at all, which importantly is different from just saying it's, that the truth is below 0. It's just we're not going to make any decisions either way about the sign of the underlying parameter theta. So I'm sure we can appeal to proper loss functions, get our 0 there, and this one just comes about by the scaling argument that I mentioned before. But to say that there's no decision, then how do we translate that into loss functions and fill in the rest of that 2x2 table? Well, we're going to argue that if you make no decision, then it doesn't matter either way what the truth is, because you haven't said anything, and therefore shouldn't be particularly more embarrassed if it's above 0 or below 0, so make those two entries the same. To make it worse to get answers wrong than make no decision, then alpha has to be less than 1, and above 0 comes from the proper loss function. So that constrains everything that's in that 2x2 table. And you get, of course, well, obviously, but it turns out you get the same Bayes rule, that you make the exciting decision when the left tail area is small, and again, that behaves like a one-sided p-value. And for students of this stuff, then you'll be familiar, I hope, with this long-standing controversy between two-sided p-values and Bayesian measures of evidence, and those two things don't agree, and Lindley's, or the Jeffreys-Lindley paradox has been floating around for years. For one-sided p-values, that doesn't happen, and there's a nice JASA paper by George Casala and Roger Berger from the 80s saying that, look, there's really quite close agreement between these things. It's not worth having a fight about, frankly. And so that's true for one-sided tests, but for two-sided tests, then what do we do? Well, it turns out you do just two one-sided tests and stick them together is basically what I'm going to do. So if we allow ourselves 3 decisions, not 2 decisions, you can be above or below, or you can just have that not proven, don't say anything exciting verdict. What would the losses for that look like? Well, there's still only 6 entries in the table. 2 of them we fixed to 0 by the properness. No decision is some constant, which I'm going to write in this way because it happens to be convenient. And then there's some number over here and some number over here. Is basically all that's going on. The product here is just to make sure that this number in the middle is smaller than either of these 2 ones. Then that's all we need to consider essentially the whole set of loss functions for this 3 decision problem when we're only considering 2 particular values of the truth, that it's either positive or negative. There's only 6 things you can do, and they end up looking like something like that with conditions that just come from making sensible decisions. One extra thing that if you force alpha A plus alpha B to be less than 1, that ensures that this otherwise decision or condition holds at least for some data sets, for some values of the posterior, some representations from the data, then it comes out that way sometimes. I'll flick ahead to some pictures based on this. What we're doing, if you think graphically, and I do, if you got some, you can imagine it sure as a function of the underlying theta parameter, and all we're really having is step functions. They go from 0 to 1 for the when you make the below decision, or 1 to 0 for the above decision. For no decision, then it's just constant. It doesn't matter what the value of theta is. You always score the same amount of loss. Take the expectation of these with respect to your posterior, and you get straight lines going up or down for the above and below decisions, and then the dash one is just constant, so you can average it with respect to anything you like, it's going to stay the same, and there it is. And that condition about these two, they turn out to be tail areas, adding up to less than 1 is just saying that, yeah, this can happen, that this, we can have decisions where we do make no decision at all. What we end up here is, yeah, a Bayes rule that says, say it's above if the left tail area is small, say that the truth is below if the right tail area is small, and otherwise say nothing at all. So that's looking if the posterior is shifted off to one side or to the other, or if it's just in the middle somewhere, overlapping 0 quite heavily, then we'd expect to make no decision in the middle there. If you have symmetry of the two losses on either side, then you get back to some stuff that looks very familiar, frankly. Some quantity that's got a p on the front. If it's less than alpha over 2, then make some decision in some direction either way. Otherwise, say nothing at all. So that's looking like a two-sided significance test. I'm motivated from an entirely Bayesian point of view through these loss functions. And there's frankly not much else you can do with this situation, so we can say that there's nowhere else to go. If you are happy to just consider the sign of the parameters, and you've got vaguely sensible loss functions about saying things are above or below and not saying anything at all, then you will end up using something that behaves in a way very similar to classical two-sided p-values, and the Jeffreys-Lindley paradox goes away in that case. But you get a whole lot of other stuff, as well as just saying a two-sided p-value. Then you can extend this very generally, and it's sort of a basis for really quite a rich framework of inference. First thing you can do is say, how risky is it? Okay, you made your decision, and you said above or below or no decision. How risky is it in different situations? And that's what I'm plotting here for these we've got red, amber, and green lines. Let's start with the green ones. That corresponds to using a weak prior or having very strong data, so when the prior doesn't matter very much, say. This is the parameter I've specified in standard error units. So if the truth is somewhere out at 2 or 4 or 6 standard error units, if it's a clear signal, say, then sure, your test based on this Bayesian posterior value, deciding whether or not it's small, that's not very risky. If you're close to 0, if the truth is close to 0, rather, then quite a lot of the time when you make decisions that are either above or below, they'll be for the wrong reason. You'll have guessed the sign wrong, if you like. And so you can do worse than making no decision alpha in the middle there. That can certainly happen as your expectation. If you have a very small signal that you're not really powered to detect, then you'd expect to be up there. For a stronger prior or weaker data, then you get a lot more information coming from the prior, and it's harder to have these small tail areas, and so you make no decision more often. So the risk stays close to alpha, the no decision risk, over a wider area, then tails down at either side. So it's a more conservative approach there. And the orange one, of course, is somewhere in the middle. Particularly interestingly, I think here, the green one, the weak prior, corresponds very, very closely to a classical Z test, like a t-test, but you know the standard deviation of the data. And that would give you the risk corresponding to the black line. And it doesn't matter what the prior is, because it doesn't use the prior in that case, but it's almost the same practically as using the weak prior strong data thing. It would give you almost the same results. If you're using that, and you happen to know that you've got, it turns out it's less than 12% power in this case. If you know you're in the middle there, above the line, then using the data and using the Z test that rejects or accepts at the usual 0.05 level is actually worse than not bothering at all. That with the loss function that I've specified, where it's the losses are, as we saw in the tables earlier, then if you're in that situation, then you might as well not bother. There's so little ability to get the sign right, you're better off just saying no decision, regardless of how the data comes out, and then you get loss alpha for the whole, however the data came out. So we get this notion of futility that it's just a complete waste of time, according to this loss function, to do analysis using the classic Z-test when you've got less than 12% power, it turns out, and that number goes up or down depending on how you change alpha, but it's always there. Sure, you can do slightly better than that if you do the full Bayesian analysis and use the prior. Then you can do slightly better. You can also work out the Bayes risk, which is the risk averaged over the prior, and you see that you get these dashed lines as I've drawn across here. And sure, they're somewhat below alpha. If you've got a very strong prior that's all centered at 0, then the Bayes risk, the dashed red line at the top there, is just very, very slightly below the risk that you get from doing nothing at all, from always making no decision and ignoring the data. And so you see that you're learning very, very little from the data, which is a useful, sensible, real-world interpretation. The data really do come out like that for some experiments. And unless you've got some hope of being able to find something, then at least for learning about the signs, then this setup is saying, don't bother. Don't bother with small, crappy, useless studies that aren't even going to tell you about the sign of some underlying parameter, in a way that's going to convince anybody. What else do I need to say here? Yeah, you do slightly better using the full Bayesian version, but perhaps not very much in situations where there's not very much data in either the prior or the very much information in either the prior or the data. For the green one, then you can see that green line, the Bayes risk there is getting lower and lower. As you make the prior flatter and flatter and flatter, that risk goes all the way to 0. And that's illustrating the fact that the prior will be saying, yeah, we're really certain that there is a ton of support for a signal which is huge off here at 2, 4, 6 or higher, or -2, -4, -6 or lower standard errors from the mean. It's always easy to find the signal, is what that prior is telling us. And that's not realistic. The world is not like that, and we don't shoot fish in barrels in that way in most work that I'm involved with, and I imagine you as well. So that's a reason to say that, yeah, that's not a real prior. It's a mathematical result, and it's ridiculous to say that you've got essentially 0 risk. We know testing is risky. We know we can get the answer wrong. If we didn't, then we wouldn't be doing the test in the first place. So we get measures of risk because we've specified a loss, then risk comes out of the expected loss pretty automatically. But so do lots of other things, and in the time remaining, I'll very briefly cover some of those. You can get credible intervals out of this. Instead of making a decision about about a single null value, which was 0 in what we were describing, then make one for absolutely every value that the null could be, every theta 0 that's on the real line, add them all together according to some measure, and say which null values would be rejected above, rejected below, or which you would just say nothing at all about and make the end decision in the middle there. Do that, and you go from this loss up here, which is just a reformulation of the tables, to this loss, which is giving you decisions about sets, and you end up with a credible interval with a formal Bayesian motivation. It's not just an ad hoc thing that happens to summarize your posterior in a reasonable way. It's the best answer. According to this loss function. Interestingly, it doesn't matter what measure pi you use as long as it's got positive support everywhere. And so we've got a Bayesian analog of its confidence interval, but we've also got a measure of optimality that goes with it. With this loss, it's the best thing to do. It's not just ad hoc sensible. You can also do multiple testing with this thing. Instead of having just one theta parameter, then imagine you've got a whole set of them indexed by j. You're going to make decisions dj for each one, and you can have that trade-off rate alpha, trading no decision against, I'm going to do a one-sided alternative here, and that tells you how we value the different decisions for each individual parameter. If we essentially add them together with a slight tweak, add together all the null losses, constant losses, regardless of the truth, when you make no decision for those parameters, and then have an indicator which says, we're really worried if we make any sign errors. For all the things that we make sign decisions about, if any of those are wrong, that's really, really bad. Score a big loss or a 1 there, or 0 if you get them all right. Then this loss, it turns out, can be used to motivate a Bonferroni correction. In particular, you need to add, if those losses there actually for the whole set, they've got to add up to something less than 1, or you get strange paradoxical behavior that you don't want going on. This motivates a Bayesian version of alpha spending. A conservative approximation to the Bayes rule in this case is to do Bonferroni correction, dividing your tail areas by the number of tests that you did. It drops out of there. It also drops out in another way that actually makes a bit more sense, which is more akin to Bonferroni's justification via the expected number of false positives rather than the family-wise error rate. And if you not met that before, then I won't go through it here, but it's very nicely described by that paper there, which is referenced in my paper. You can also, again, it's not my work, but you can use the same sort of idea about trading off things where you make no decision and things where you make positive decisions to get a Bayesian motivation of the Benjamini-Hochberg algorithm for doing false discovery rates, and they have a Bayesian meaning as well from essentially the same summaries, summarizing data in essentially the same way. You can make silly jokes about sheep and get Bayes factors out of this machinery as well. You need to invent a clone parameter, but after having done that, then you're basically setting up it's now you've got a clone parameter, so there's 4 different things that the truth can be, and if you just have 2 decisions, you've got a 4x2 table to fill in. If you fill it in some particular way, and it has to be rather specific, it turns out you can get Bayes factors out, or use of Bayes factors out as a Bayesian decision rule. Why is this useful? Well, for people who like Bayes factors, then it gives you a new interpretation of the cutoff values for Bayes factors. They're weights of evidence in favor of odds ratios sort of measures comparing the null and the prior and the posterior for our parameter, and whether it's positive or negative. At the moment, if you look in something like Cass and Raftery's landmark Bayes factor paper, then they say, the Bayes factor, this ratio thing, if it's between these values, then that means you've got sort of strong, weak evidence. Well, they never say what that means. It's sort of t-shirt sizes that you can be small, medium, large, or extra large, and no one knows exactly what that means. It just looks a bit like a t-shirt, and it happens to be bigger than the other size. Here you can say what it means in terms of a loss function. The function comes in, and it's a comparison in the sense of making no decision to making a positive decision and getting it wrong, basically. So you get an interpretation there for the Bayes factor meaning, which is new. You can also get an interpretation of the two-sided p-value itself as a Bayes rule, where you're comparing, if I had to make trade-offs between these sorts of losses, these indicator functions that kick in if you get things wrong, basically, or if you just make no decision, what would be the best way to trade off those losses? And that sort of dual problem, if you like, it turns out motivates the two-sided p-value itself as a Bayes rule, and not just whether or not it's bigger or smaller than some threshold alpha. It's a little bit more tenuous, I think, than the rest of the stuff that's in the paper. That gets you close to severity, a recently proposed measure of what's warranted and what's not from a significance test. It's fairly controversial stuff, I think, severity, so I won't go into it here, but we can get something that behaves quite like it from a Bayesian point of view, where we're saying what the measure of optimality that goes with it is. So I'll sum up there, and this is a real sign, which I really like. It's not in use. God knows what it means. But if you're going to just say that, and I think you can introduce this to really introductory statisticians, real beginners. If all we're saying is that some parameter is either positive or negative, they can understand that and not mangle it too much, and use that to understand p-values. It could be a useful way to introduce them. It also forces them to think, why am I doing the analysis? I was at a very good talk this morning on graphical communication, but make people think about the question. What do you want to answer with your data analysis? And if it's not that theta is positive or negative, then what is it instead? And give them some language for doing that, which I think we currently don't do when we present p-values and confidence intervals and such like. I find the normative aspect helpful. It tells you what to do. After you've got the loss function set up, there's basically nothing else. It's just computation after that, and that's straightforward to do in many situations. It's certainly not a panacea. It's not going to solve all problems. I haven't specified what evidence means, and sure, if you're out there lying and cheating with your data, then this is not going to fix it, and I don't pretend it is. very interested to see what the discussants say, but I do want to acknowledge a couple of students with whom I worked on this work. It was Tyler's master's and it's Chloe's PhD work. Also a laundry list of other people who've made useful comments, including the referees and editors. Referees, if you're out there, then thank you. It was all very helpful. And the funding. So I'll stop there and hand over to Leo.
Thank you very much, Ken, for a beautifully timed presentation. So I'd now like to call on Leonhard from the University of Zurich to present his paper on a new standard for the analysis and design of replication studies.
Thank you so much, and thank you for having me here. It's a great pleasure to present this to you in this discussion meeting. So I will be talking about replicability of research findings, which is crucial for the credibility of science. And over the last years, large-scale replication projects have been conducted in various disciplines. And these projects help to assess what extent results from original studies can be confirmed in independent replication studies. And as probably many of you know, in some disciplines, actually, the replication quote was rather poor, and some people even talk of a replication crisis. And so, for example, at my university, we have the Center for Reproducible Science that I'm heading, that just got formed a year ago to help to improve replicability of all empirical domains of science. So this is a center really across faculties. So to set the scene, I want to talk a little bit about the analysis of replication studies and what the current standard is. So here you see, very simplified, how that looks like. So we have an original study which gives us an estimate, an effect size, so that could be a mean difference or log odds ratio, whatever you prefer, with a confidence interval, 95%, and a p-value which is quite small here in this case. And now a replication study is conducted, and that gives basically independent evidence on the original study, and in this case you get the corresponding result over here. Okay, so to set the scene, here's some notation. Theta hat is my effect estimate, sigma is the standard error, n is the sample size, and p is the p-value, and then I have the index O for the original study and R for the replication study. So what do people do these days to assess replication success? So probably the most common approach is just to assess significance of the replication study, and if the original study was also significant, then people declare replication success. This is similar to what's called the two-pivotal study paradigm, which is used in drug approval, in drug development and drug approval by the FDA or EMA, which requires two significant studies before a drug is approved. However, you may also look at effect sizes, right? And in this example, you'll see that the effect size in the second replication study is smaller than the original study. So you may wonder, well, maybe the original study was actually exaggerated. Maybe it was due to publication bias or other questionable research practices, and so you may wonder if you can really call this a replication success. A third approach that's used is to do a meta-analysis of original and replication effects, and that gives us a combined effect estimate. But that's not really what you want, because when you conduct a replication study, you want to question the original study. You're not sure if it's correct. You don't want to take it as face value. And so that has kind of motivated the work I want to present to you here now today. So this new method that I'm presenting is a combination of what's called the analysis of credibility, a method that has been proposed by Robert Matthews already in 2001, and the assessment of prior data conflict, which goes back to George Bock's 1980 paper. And this combination leads to a new definition of replication success and a new p-value, right, which I call the skeptical p-value, to quantify the degree of replication success. And it can also be used for the design of replication studies. So at the end of my talk, I will briefly mention ways to calculate the power for replication success and to calculate the sample size of a replication study to achieve a certain power. Right, so just to revisit the example so that you see what's happening here. So this is the example again, and the new bit now is here in pink, PS, so this is the skeptical p-value, and you can think of it just like an ordinary p-value. So it's 0.083, so the smaller, the larger is the degree of replication success. You can also threshold it, so for this particular p-value, we would have replication success at level alpha 10%, but not at level 5%. Okay. So let's dive a little bit in the theory and how the skeptical p-value, where it comes from. And so to understand the skeptical p-value, we have to understand skeptical priors. Okay, let's go back to the original study, which gave us this effect estimate with this confidence interval. And let's suppose we don't trust that, right? So we apply a skeptical prior. That's an old concept, which you see here on the right, centered at 0 with some variance, and you combine it with the original study that gives you this posterior here, right? So you see, informally, the posterior is still significant, but it's shrunken towards 0 because of this skeptical prior. By the way, throughout this talk and also throughout my paper, everything is normally distributed, so the skeptical prior is normal, and also the effect estimates are all assumed to be normal. Now you can bring this one step further and ask, well, how skeptical do I have to be such that the posterior is no longer, in quotes, significant? This is Robert Matthews' idea from the analysis of credibility. And that brings us to what I call the sufficiently skeptical prior. So it's sufficiently skeptical such that the posterior is no longer significant, in quotes, right? So we fix that quantile here at 0. By the way, I think I forgot to say that this is a bit more general, so the confidence intervals, they don't have to have level 95%, so they're general, level 1 minus alpha. Okay. So the idea is now really, we challenge the original study with this sufficiently skeptical prior. And this is, in a sense, step 1 of the proposed method, and it's a reverse Bayes approach. And that's a method which is not so much used, which I think should be used more, and which goes back to Jack Good. It's mentioned already in one of his books in 1950. And later in 1983, in this book, Good Thinking, I found this quote which summarizes reverse Bayes. So we can make judgments of initial probabilities and infer final ones, or we can equally make judgments of final ones and infer initial ones by Bayes' theorem in reverse. Right? So that's what I do here. Instead of applying forward Bayes, prior times data gives me the posterior, I do reverse Bayes. I fix the posterior, or in this case, a property of the posterior, and I compute the prior that combined with the data leads to that posterior. Okay. So that's step number 1 of my new definition of replication success. So think about it as there's a skeptic who argues that the original effect combined with this sufficiently skeptical prior would no longer be significant, right? Now, step number 2 is the following, right? So now we do a replication study, which you see here in green. And if that replication study is in conflict with a sufficiently skeptical prior, then I declare replication success, right? So then basically we have shown that the sufficiently skeptical prior is unrealistic because I've done a replication study and it's in conflict with that prior, right? So that's the idea. And of course, now the question emerges, well, how do we measure conflict between a prior and some data? And that brings me to George Box, who presented this idea in 1980, also in a red paper, also published in Series A. And he suggested to calculate a tail probability, so something similar than a p-value, a prior predictive tail probability, which in this case has the form that you compare a chi-squared distribution with 1 degree of freedom against the replication effect estimate squared divided by the prior predictive variance, which is the skeptical prior variance tau squared plus sigma r squared, the squared standard error of the replication study. Okay? So you get this p-box, and now if p-box is smaller alpha, and it's the same alpha that I used earlier for the level of the confidence interval, then I declare replication success. Okay, so that's kind of the machinery. So going back to the example, if I have a level of 5% alpha, 5%, then p-box turns out to be 0.098, right? So I have no replication success. P-box is larger than alpha. If I instead use 10%, then actually p-box is smaller, so p-box depends on alpha. That's maybe surprising, because the skeptical prior variance depends on alpha. And in this case, we have replication success. Okay? And now it's natural to search for that value of alpha where we just about achieve replication success. All right? So again, similar to p-values, which are basically just 1 minus the confidence level, which is just significant, we do the same here. And so the skeptical p-value is the smallest level of alpha where we are able to declare replication success. Okay? And in that case, the level alpha is actually the same as p-box. Right? So this explains where this skeptical p-value comes from. Okay, so now you can actually dive into math and look at properties of the skeptical p-value. And it turns out, actually, it has quite nice properties, and basically everything can be done analytically. And so let's look at this in a bit more detail. So you can transform the skeptical p-value, ps, to the corresponding quantile, which I call ZS. And it turns out there's a quadratic equation from which you can compute ZS squared, which is shown here, which can be solved analytically. So let's have a look what's actually relevant to calculate this number. Well, the first thing is TO squared, so that's just a test statistic from the original study. So that's essentially just the p-value from the original study. Then we have the test statistic from the replication study, again, the p-value from the replication study, so both enter here, plus on the right side you see C, which is the relative sample size. So that also enters. The relative sample size is the sample size of the replication study compared to the original study. You can also describe this with the corresponding variances, which I did actually in the paper, but in this presentation, to keep it short, I did it with the relative sample size. Right, properties of the skeptical p-value. Well, the first property is not so surprising, but it's reassuring that it does something useful. So the smaller the ordinary p-value is, the smaller the skeptical p-value, right? More interesting is already the second property. The skeptical p-value will always be larger than both ordinary p-values. So it's more stringent than the 2 pivotal study paradigm, which I mentioned earlier. And actually, if you fix the p-value, and if you let C go to 0, the relative sample size, then you actually reach that limit, and that will be important in a minute. The third property is that the skeptical p-value naturally extends the ordinary p-value of the replication study. And it does this by taking into account the uncertainty of the original effect estimate. So what does that mean? If you ignore the uncertainty of the original effect estimate, then you just have a point mass, right, for the original study, and you need a skeptical prior, a point mass at 0, right, to push it towards non-significance in the limit. And so box tail probability just reduces to the ordinary p-value for a point null hypothesis, right? And this is written down here in mathematical terms. So the skeptical p-value converges to the p-value of the replication study if the original standard error goes to 0. The nicest property of all of them is the fourth one, right? Because that's something where ordinary p-values fail, and they are often attacked because p-values don't take into account effect sizes, right? The skeptical p-value does take into account effect sizes, right? And to be a bit more specific, it takes into account the relative effect size. So to explain this, I just want to give you an example where both studies, both ordinary p-values are 0.01, original and replication, and in the top picture, the effect estimates are also the same, right? So they are 2, and in this case, it turns out the skeptical p-value is 0.069, right? Now look at the bottom picture, where the p-values are still 0.01 in both cases, right? But the replication study gave us a smaller effect estimate, just half as large as the original study. So there was substantial shrinkage, same amount of significance, but substantial shrinkage, and you see the skeptical p-value gets larger, right? 0.14, it reacts to this. It doesn't trust that result that much. So that's quite a nice property, and it brings together the two ways to analyze replication studies, which I mentioned at the beginning, looking at significance, but also looking at effect sizes. And it brings it together in one quantity. Thank you. Yeah, so now you can look at various things, distribution under the null of the skeptical p-value. So here you see the distribution of an ordinary. This is the two-study paradigm if C goes to 0. And now you see the distribution of the skeptical p-value under the null. You can compute this through simulation, and you see the larger the relative sample size, so the larger the sample size of the replication study, the smaller the risk of a false positive finding. So that also makes sense. However, we have to fix one thing, which is coined the replication paradox. And this is illustrated in this picture. What does this method do if the replication effect estimate is significant but goes in the wrong direction? Right? Because of the construction of box tail probability, which doesn't care about the sign, the skeptical p-value will be also small, right? So it would also declare this as replication success. So that's obviously something you don't want, right? And can you fix it? And the answer is yes, you can. I have to be a bit quicker now. You can fix it, and you can from the same principles that I detailed to you, but using now one-sided confidence intervals and a one-sided assessment of replication success, you can derive a one-sided skeptical p-value, and as it happens, it turns out to be just half as large as the two-sided one, if the signs are the same. However, if the signs differ, then it's 1 minus half the two-sided one. So you see here, the two-sided one was 0.02, the one-sided one, because it goes in the wrong direction, is actually 0.99. So you can fix that paradox. The last 3 or 4 minutes, I want to move now to a scenario where we just have an original study, but we don't have a replication study yet, okay? So what do we do now? And you can apply the same concept now to define something which is called intrinsic credibility, again originally proposed by Robert Matthews, to to assess the conflict of the original study with a sufficiently skeptical prior in the absence of a replication study. And if you do this, and I've written this up in a recent paper here in this year, you actually end up with a new threshold for intrinsic credibility, which turns out to be 0.0056 two-sided for the 5% level. One-sided, it's 0.02. And I mention this here because it will be important in a minute. Okay, so now let's move on to the design of replication studies. So we can, for a given original study, now do power calculations and sample size calculations for the replication study. I do this a bit faster, otherwise I get in trouble with Paul here. So let's suppose we just repeat the same study with the same sample size. Relative sample size is 1 at the 5% level. What's the power? Well, the traditional power for significance. Well, that's just a function of the two-sided p-value, which you see here in the original study. And it's a well-known result, which I think was first published by Steve Goodman in 1992, that if your original p-value was just borderline significant, then the power is just 50%. So if you repeat the same study and your original p-value, which is 0.05, the chance to get a significant result is just 50%. And you can actually distinguish two cases, conditional and predictive power. No time to discuss this in more detail. So the question is now, well, how does this work now with my new concept of replication success? Well, here we go. It drops quicker down to 0. And there's also a magic point where the two lines cross at 50%. And it turns out, and the proof is in the paper, this is just the threshold for intrinsic credibility. So this is just this 0.0056 number. So what does that mean? So that basically means if you have an original study which is only suggestive, which is just borderline significant, then actually with this concept of replication success, it will be very difficult to achieve this. However, if you have a very small p-value in the original study, then the power will be, at reasonable levels. You can also do this one-sided, and you could argue maybe one-sided is better, then it's less extreme, but it's still below this curve for significance. And now you can turn this around and compute the relative sample size for a fixed power, and those are also the figures from the paper. This is what it looks like if you power for significance. This is what it looks like if you power for replication success, two-sided or one-sided, right? So that means if you want to achieve, this is for 80% power, if you want to achieve 80% power and your p-value is just a borderline significant, you have to increase your relative sample size very much so to achieve that value of the power. So it's a quite stringent criterion. All right, to finish up, here's a quote from David Spiegelhalter. P-values are just too familiar and useful to ditch, right? So this work is really in the spirit of this quote. Let's try to do something with p-values that gives us more insight on things that are relevant in science, like replication studies, right? So what I presented is really evolution rather than revolution. So I don't want to abolish p-values, but I use p-values to bring in a new concept and to get more insight from replication studies. And the things I'm using are just standard things that everybody is reporting in these studies: effect estimates, confidence intervals, sample sizes, and test statistics, and the corresponding p-values. There is an application, I'm not sure if the discussants will comment on this in the paper, where I don't have time to dwell into, where I look at this replication project from psychology, where 100 studies have been replicated. So please read the paper. And there's also software which I invite you to use. So it's available on R-Forge, and it's called Replication Success. The link is in the paper. And so you can compute all the things that I mentioned here with this package. So thank you.
Thank you very much, Leonhard, and beautifully to time. So it gives me great pleasure now to call on the proposer of the vote of thanks, Adele Marshall, from the Queen's University Belfast, which is particularly appropriate given where we are. So Adele, would like to come up and propose the vote of thanks.
First of all, it gives me great pleasure and a real honour to be invited to give the vote of thanks this evening, and to two very intriguing papers. And I have a slight confession that I have, in my original timetable, them in the other order. So I'll talk about them in reverse order, so you'll see that in my slides that follow. But before we go into that, I want to just thank the Royal Statistical Society, first of all, for coming back to Belfast, and welcome all to Belfast if you haven't been here before. It was 2006 when we last hosted the conference here, so it's great to have you all back. And also to thank the Royal Statistical Society for actually choosing these two particular papers, because I think if you haven't discovered it already during the presentation so far, both are contributed significantly and are of great value as we will discuss it further. So as I said, I have them in reverse order, and just before we start talking about the papers, it occurred to me that a lot of what the models that we are currently building and the challenges that we currently have are all about, you need a model that you can justify, you have to be able to explain it, everybody wants to do AI, so we want models with AI in it. We want models that can help us make decisions, so we want actionable models, we want explainable models, justifiable models. All of these characteristics play an important role. And of course, things that are repeatable and reproducible as well. And that brings me nicely to the first of the papers that I will be discussing, which is Leo's paper. My slides are really very brief, so they're really just highlights of the paper itself. But before we start, I went off on a mission to look at reproducibility and to see what do we need to do? Is it just a case that we take the same data, give somebody else the code, and reproduce it? Is that what we mean by this in the paper? And there's lots of discussions, and it's been going maybe for the last 3 or 4 years about reproducibility and about this issue that it goes beyond that. It's not just about taking the same piece of code and data. It's beyond that about taking another data set and seeing whether the same outcome or conclusion can be drawn from that. And we even embed this ourselves into our very own journals, where we want a certain level of reproducibility in our scientific work. But as I said, this goes beyond that. It means that we can bring new data in and get new information. To say a little bit then about the contribution of this paper, I must say I find it something that could be of extreme value beyond the actual context in which it's presented. We talk of the author, the previous speaker, has talked about the skeptical P-value, but then really explored and expanded beyond that in terms of, well, what about looking at reverse Bayes? And initially, it seems, whenever reading the paper, it seemed quite intuitive to do this, but obviously the thought had to be there and to come up with the idea in the first place. But as you can see, it's very effective, and it's, to me, reasonably intuitive for someone without that background knowledge to be able to comprehend and understand. To me, and the main contribution I feel this makes, is that it adds a scientific metric to the way we can acknowledge or represent reproducibility. So there's been lots of discussion, it's quite vague and fuzzy, whereas this actually gives us a quantifiable way of measuring reproducibility. And as I said, once you read the paper, if you haven't already, and you see the illustration and the example, I think it becomes quite intuitive. And well, all those highlights and points that were said already by the speaker are properties of being able to use it in this way. But also, just as a closing comment, I just wondered, can we expand it much further? Can we use this to help those working on all the AI models that are out there to actually have something that's reproducible for them also? So thank you for your contribution for this paper. Now I'm going to talk about Ken's contribution. And again, this goes back to the challenge of, okay, we've got our data, we want to create a real-life model, we need it reproducible. Well, we've covered that in the first paper, but we also want something that can be quite actionable and we can make decisions on. And I think this is the nice intuitive aspect of this paper, where we can bring in the decision science element and have that loss function that we incorporate in the model. Again, a lot of this has already been discussed today, so I'll not go through the highlights again, because the author has done a very good job of that themselves. But some aspects, I think, are worthy of highlighting just again, and that's the idea of something simple like sign. Everyone can understand it and get the grasp of that. The fact we said earlier about the decision and bringing in the decision theory, and also that it can appeal to non-experts. So you don't need to be fully versed in the whole area to possibly be able to use it. And it's encouraging that critical thinking, which is that other aspect of having models that are actionable. I did go in and give some nice examples, because to me this was quite straightforward, and everybody as a statistician will follow this example of having our single parameter that we're interested in, looking to see if it's above or below 0, and that decision of whether it is A or B, above or below. And if we can look at theta being greater than 0 and the decision being below, then that gets a measure of alpha, which to us will be a reasonable way of representing it. And likewise, the reverse, if it's alpha or theta is less than 0, then and the decision is above, again, that works out to be 1 minus alpha. So that's very intuitive and like common sense to the statisticians. And of course, then we explore other examples. And if you look at the paper, there are many other examples of where this can be applied. And as the author had mentioned before about Bayes factors, and it's just the example that I'd illustrated there as well. So just my final comments on the first paper. So Ken's work, it brings in that decision theoretic framework. There's just a multitude of examples there that have been included in the paper, but it's not an exhaustive list, as the author has already recognized. And it's fitting into that whole remit that's expected of us as statisticians and our models in today's society, where we have to have explainable, justifiable, repeatable, and actionable. Okay. Thank you again to the authors, and that concludes my discussion.
So I'd now like to call upon the seconder of the vote of thanks, Jane Hutton from the University of Warwick.
Thank you very much for asking me to second this article, these two papers. And sorry, I've got one or two quotes that I might throw in, hence the laptop. So thanks for the very stimulating articles. I very much feel, particularly at a conference like this, that we're all far too busy and we don't have time to learn from other fields as much as we should. So when we think about knowing the signs, yes, it's good to have. I've picked up some quotes that particularly struck me, specify the exact questions being addressed, test a hypothesis about the sign of a real univariate parameter. Sounds like quite a good idea to me. There wasn't that much on estimation, but we did get a bit of a look at power and risk and severity and some of the concerns about multiple testing. And in terms of the ideas of analysis and design of replication studies, there were some other things that particularly struck me. Can claims of new discoveries be confirmed? Is there no established standard for statistical evaluation of replication? Is it natural to ask how skeptical we would have to be? The original study is credible if the absolute value of the effect estimate from replication is within certain limits. What about intrinsic credibility? Credibility of out-of-the-blue findings without any prior support. The Bayesian assessment of sample sizes. And yes, I am going to mention the open science collaboration, a multi-year endeavor that replicated 100 scientific studies in high-ranking journals. How exciting. So what is the question? As far as I'm concerned, we have a question, to P or not to P? That is not the question. That really is not the question. If you have looked at replication, to P or not to P is not the question. Let's go back and have a look at some of those highlights I mentioned. No established standards? Well, actually, the European Medicines Agency, the Food and Drug Administration, Committee on Safety and Medicines, things where it actually matters, there's been quite a lot of work done on what we take as replication. If you want to say, look, I've got another drug, it's much cheaper, but it's as effective as the first drug, yes, there is a standard for what that means. And is it really true that the original study is credible provided the absolute value of the effect estimate overlaps? Well, but how does that effect estimate arrived at? Was that effect estimate arrived at by excluding a quarter of the data because it didn't fit the theory? I hope you'll realize I'm not joking. This is the kind of thing my PhD student is up against in behavioral economics, that minor discipline which now informs governments in the USA and the UK. The intrinsic credibility of out-of-the-blue findings? Well, actually, I wrote about selection biases about 20 years ago, where you get people who did these studies and then they looked for the most significant of the 20 or 30 things they measured and they reported that. Actually, it's not very difficult to work out that the distribution of the maximum as opposed to of a series of values instead of distribution of a single value. Hutton-Williamson is about continuous measures. Hahn, Hutton, etc. is about subgroup analyses in the context of meta-analysis, but it's equally applicable. The Bayesian assessment? Well, actually, about, 20 years? Well, yeah, 25 years ago, certainly quite some time before O'Hagan and so on, I wrote a paper about how you might think about writing your samples, selecting your sample size if you were Bayesian, and you said to people, what do you think about this? Deborah and I shared an office for rather a long time, and she was there when somebody turned up saying, our new treatment appears to be killing patients. It was doing quite a good job at killing patients, and there wasn't a mechanism of stopping the trial. If you'd looked at the priors there, you would have found quite a wide range of beliefs, and you might have asked the question, what evidence do we need for people's beliefs to converge? So maybe you need to think about that. Now, the open science collaboration, I've read some of this stuff. Be a good idea to sort out the ideas of replicating, repeating, reproducing, recording things. And in fact, Andrew Gelman's given quite a nice discussion of this. And my comment about learning from other disciplines is because this is social sciences. Medicine is different. So over 50 years ago, it was pointed out you can have a whole series of studies which never prove or disprove anything, but you can get your chair at Harvard out of it. Then Cohen sort of pointed out that actually maybe you should think about design, power, data collection. Zwerzi and Kahneman said, well, unfortunately, researchers' ignorance about uncertainty and variation and their beliefs in what they do has some rather unfortunate consequences. But that got forgotten. And then gradually we get some concern about significance testing and false positive psychology. And then we get the open science collaboration. We replicated papers published in high-ranking journals. Okay. P-values are a really easy target. They're great fun to play with, but that's actually not really the problem. And Leek and Peng, and pretty well anybody in this room, can do the same thing. Before you get a p-value, you've got to think about your study design. That means you've got to think what the question was. What analysis are you going to do? What's your data collection? What's your data monitoring? Do you verify your data? Do you clean your data? Do you document everything you do, or do you throw away the half of the data that doesn't fit your theory? Carbon dating, by the way, when I looked it up, yeah, they got a straight line to fit through, and so they could get the dates, but that was done by throwing away half the data. Exploratory data analysis, what's actually in there? And a PhD student of mine has said the great thing about those medical statisticians who are older than I am, who paved the way, is table 1 in papers. Your first table should say what is in the data set and how many people. Not very common. How about fitting models, checking them, checking the interpretation, summarizing the effect sizes? Maybe p-values might have a role here. And the implications for future study. Is that done? Well, how would you replicate a study if the published article does not give the aims, does not give the study population, does not give the design? And is it even worth replicating? Wilkinson and a task force on statistical inference made recommendations in 1999, and my student Kenneth came up with a checklist. And we took a random sample of 30 of those papers that you've seen the picture in Lennon's paper, and scored them. Double scored, so he evaluated them, they were secondary evaluated, they were verified, there's some replication. Let's have a vote. How many of those 30 scored greater than 80%, do you reckon? Any offers? How many of those papers scored greater than 40%? Right. Bad luck, Peter. You were right in the first answer, you were wrong in the second answer. Do you want to try the second answer again? Wrong direction. 0, right? Not one of those 30 papers scored even 40%. Of course, we can't get it published because the answer is, oh, well, you didn't look at all 100 papers, so maybe we should think about a p-value. If 0 out of 100 gets something, what's the probability that the remaining 70 scored above 40%? Were the questions we were asking unreasonable? Well, here's one of the questions derived from the Psychology Association's own task force. Was the sample representative of the target population? Target population? What do you mean, target population? One of these studies that was replicated, which concluded our data suggests that change detection is based on different mechanisms in audition and vision, was based on, wait for it, 4 people. 4 people, 2 of whom were the authors. Oh no, there was one study where there were 3 people. Right? Look at that conclusion. Now, when Kenneth has complained about that, he gets told, well, don't be ridiculous, all people are the same. We don't need to have more than 4 people. Do you need a hearing aid? Are you happy for that to be tested on one person because all people are the same? I have this vague idea that as I get older, my hearing is not quite the same. So what is science? Why are we talking about p-values when a high-ranking journal is publishing studies based on 2 authors, 2 people and their students, and about listening and drawing conclusions about vision? Where is the argument about p-values in that? The quality of reporting really does need to improve, and before we can say anything about whether the quality of studies needs to improve, We actually need to know what's in the studies, but I bet we really need to improve the quality of study design. And it would really be quite nice if we didn't spend too much time reinventing the wheel. Try looking at the equator network that all my worthy and dedicated medical stats colleagues have done. What do you need to put into a study? How can it be replicated? Should you pre-register study? Should you decide on publication, not on p-values, but whether the study was designed with any intelligence whatsoever? Oops, sorry, I wasn't meant to be quite so sarcastic, was I? And then again, it was very disappointing to hear this morning from USA colleague Rochelle Trachtenberg that apparently ethics institutional review boards in the USA don't listen to statisticians who say the study could never achieve anything. Well, never mind. The scientists are important, so what does it matter if the study's worthless? So I appreciate these papers very much, but I think we've got an awful lot of work to do.
So the tradition I didn't explain is that the proposer is usually fairly complimentary, and the job of the seconder is to raise lots of challenging issues, and these two clearly knew their roles. So the vote of thanks has been proposed and seconded, so I'd like to put to the meeting in the usual way. Could we show by a round of applause? Now, we're going to the discussion part of the meeting, and we'd like to take people at the meeting first. So I'm going to take Paul. Has anybody raised with you recently that they'd like to give a verbal presentation? So, Peter? So, is there any others who've raised it with you? Okay, so Peter, come up. After Peter, I shall ask for anyone else to indicate by showing their hands that they'd like to talk, and we need people to come up here to say their words, and then if there aren't, then we'll move to the written contributions. But Peter Diggle, University of Lancaster.
Yes, yeah, intriguing papers, thought-provoking papers. One property of a skeptical, I've got two questions and then a general observation, and they're more obviously directed at Leo's paper, but one or two of them might have an indirect bearing on Ken's paper as presented. One property of a skeptical p-value, and originally I put one very sensible and then I crossed it out, is, as its name implies, it can be no smaller than its corresponding standard p-value. And I asked a question which Leo partially answered in his presentation, which is what would be the relationship between the two, the ordinary and the skeptical p-value, if the original and the replication studies were identical, both in design and in the data they produced. Now, you may say that shouldn't happen, and I agree. I mean, the first conclusion should be that somebody's cheating. But as a limiting case, it kind of makes you think. And something at the back of my mind suggests that if studies are, in some sense, perfectly reproducible, then surely that reproducibility strengthens the original conclusion rather than weakens it. So there's something I don't understand there, and I'd like Leo to clear it up. The second thing, which again I wrote this morning when I was preparing these comments, that most statisticians would agree that as a general rule, estimation is more interesting than testing. I like the authors, have no wish to abandon p-values, but equally, I do think on balance, estimation is usually more interesting. And so immediately I thought, well, how would you define a skeptical confidence interval? And having defined it, would the duality between standard confidence intervals and p-values translate to their skeptical counterparts in some way? And if so, how? Now, the more general observation was really prompted by the fact that Leo's paper spent quite a lot of space talking about power. And again, this issue came up in Ken's paper. If you take the context of randomized clinical trials, where I think significance testing is perhaps better entrenched than in many other branches of statistics because of the regulatory nature of randomized trials, certainly in the drug world, because I always think of significance testing as almost like a court of law where you're innocent until proven guilty, or perhaps in the trials context, you're guilty until proven innocent. But so that in that sense, although scientifically the logic behind significance testing is a bit back to front, you can see that it does have a fairly natural, I think, basis in regulatory settings. But in that context, I really don't like sample size calculations to focus on power. I'd much rather they focused on precision of estimation. And there are two reasons why I think this. Firstly, it avoids what seems to me to be a particularly arbitrary value that you have to set for the power when your effect size is at the clinically significant difference. I mean, frankly, my empirical observation from a number of short collaborations over my career is that clinically significant difference usually means the difference people hope to find rather than what is actually clinically significant. But I genuinely don't know, and I don't know if either of the speakers do, where did the 80% convention for an acceptable level of power come from? Now, Ken's theory, if I interpret it correctly, does actually give us a little bit of light on the notion of futility, but where did 80% come from? Now, the more important result for me, and I'll be very happy if somebody can explain why I'm deluded here, because I have the greatest respect for people who design and analyze clinical trials, and there's something I'm not understanding. Because I have never understood why a significant result in a conventionally powered trial should be regarded as a positive result. Because if the clinically significant difference means what it says, in other words, it represents an effect size large enough to be on average of material benefit to the patient, then shouldn't you only declare a positive result when you've actually got some degree of confidence, and I'm using that word in its dictionary sense rather than a technical sense necessarily, you actually have some degree of confidence that the actual effect size is at least equal to the CSD. And rejecting a null in a high-powered study has no relationship whatsoever to that. So, you know, really, I enjoyed the papers. I do apologise to both authors. I had to read them rather quickly, but I thank them both for their exceptionally clear presentation, which really gave me a lot to think about. And that's it. Thank you.
Thank you, Peter.
I should also like to thank the speakers for their excellent presentations. I haven't had an opportunity to read the papers yet, but I wanted to make a couple of comments. First of all, on Leon's, the notion that in the replication study, one has a sort of prior expectation, particularly if it's a first discovery, that the effect size might be lower, and you would expect to be lower in your replicate study. And as a rule of thumb, I've generally used about half. And so I wonder if there is any link, which would mean that your replication study would have about 4 times as many individuals in it as your original study, as a sort of rule of thumb. And linking that rule of thumb to a suggestion, at least, in response to Peter's question, where does the 80% come from? I think the fact that a rule of thumb for working out study size is that if you've got 80% power, 5% significance level, then the 0.84 plus 1.96 squared gives you 8. 80% power, it's a nice mnemonic, and half that is 50% power. And if you can't design a study that hasn't got at least 50% power for the plausible effect size, go do something else, is my explanation of where 80% power may have come from. My third point, again to Leonhard rather than to Ken, is if in fact my replication effect size is larger than the discovery effect size, should I be surprised? Thank you.
Thanks. We have quite a number of contributions that have been sent in writing, and I'm not going to read them all, but I'll stop me if I go on for too long. I thought I might do 4.
Okay, no, that's
Is that all right? Yeah. Okay, so the first one is from Professor Christian Hennig at the University of Bologna and University College London. I enjoyed reading the paper by Rice, Bonnett and Krakauer, and I agree that it gives a new view of two-sided tests that can contribute to their better understanding. What the paper develops, however, is its own method, closely related to tests and p-values, but not the same. Therefore, I think that it's wrong to claim that it gives a new motivation for two-sided tests and p-values. I disagree with the not very elaborate criticism that point-null hypotheses are usually scientifically implausible, and hence only a straw man, that motivates the claim that two-sided tests lack a proper motivation. Starting from the idea that all models are wrong, it should be clear that when testing a point null, we cannot attempt to confirm its truth. I therefore object to the term accept for interpreting non-rejection. Rather, the question is whether the observed data are compatible with data generated from the null hypothesis in the sense defined by the test statistic, in which case they cannot be used to claim evidence for anything else. This is what the two-sided test addresses. I don't have any issues with it that would require Rice et al.'s motivation to sort them out. I don't see why considering a point-null hypothesis is worse than relying on a parametric model in the first place. If this is required to hold literally, it's also clearly unrealistic. I think that a major issue with statistical tests is that they're usually interpreted in terms of deciding what the true model is, either the null or the alternative, rather than taking explicitly into account that models are helpful tools for thinking rather than true reflections of reality. The author's Bayesian approach doesn't help with that because it's based on prior and posterior, often interpreted misleadingly as encoding probabilities that certain models are true. The method presented by the authors has its own merits and interest. However, in my view, two-sided tests are just fine without it, if interpreted carefully. The next one is from Nick Longford. I wholeheartedly welcome the author's proposal to engage decision theory in problems that are at present addressed by hypothesis testing. The end product of a hypothesis test of any consequence is the choice of a course of action, either the one associated with the hypothesis or one with the alternative. That is a decision, and we all agree that hypothesis testing is neither suitable nor intended for making decisions. In variance with the authors, I endorse the statement of Cox as factually correct, but regard it as grounds for dismissing hypothesis testing from statistical practice altogether. Unfortunately, the authors do not involve in their discourse the client for whom the analysis is conducted and who wants to inform their agenda by statistical analysis. An analysis is distinctly second-rate if it ignores the client's perspective, value judgments, priorities, or remit. Outside the confines of statistics, we make decisions in the presence of uncertainty by weighing the hypothetical probabilities of inappropriate choice, as done in hypothesis testing, and integrating them with the consequences of the two kinds of error that may be committed. Hypothesis tests and any other method that is oblivious to these consequences is inconsequential, and that disqualifies it from modern statistical practice. Arguably, the use of non-informative priors is another example of such disqualification. Is there really no prior information? The rationale for being Bayesian is to use such information, but then we declare such information to be vacuous. The eye of the analysis is firmly off the inferential ball. Treating all biomedical applications with one alpha and those in physics with another, from section 1.1, is too crude and simplistic. If adopted, the author's proposal will ossify into a new computational ritual unless we engage the client in the formulation of the loss function. This is not a technical methodological problem, but one of the prevailing scientific culture in which we abdicate the responsibility to tailor the details of the analysis to the client's perspective and fail to conclude the analysis by a proposal for what to do next. Choose one of the contemplated courses of action. Hypothesis testing is of immense historical importance in statistics, like the steam engine is for locomotion. That's a good thing for finding it for it a prominent place in a museum. I think the next couple that I'm going to read are not projectable on the screen, so you have to listen to me instead of hearing them. So one from Maya Mathur and Tyler van der Wieler at Harvard University. This is addressing Leo's paper. To assess replication success, Held quantifies the extent to which a Bayesian prior on the original study's effect would need to be skeptical in order to shift the credible interval to include the null, and then considers evidence from the replication against this prior. His methods sensibly represent asymmetrical information between the original study and replication, and they account for the magnitude of the replication's point estimate, not just its statistical significance. We consider these methods best suited to replications of inherently implausible original findings. Otherwise, they may be conservative. A prior mean of 0 is suitable when, a priori, the most likely effect size is 0, and effects in either direction are equally plausible. In these cases, the replication may indeed provide the only source of evidence against the sufficiently skeptical prior. However, in many replication contexts, the original studies likely have true effect sizes larger than 0. Open science collaborations replications suggested R was 0.197 on average, bigger than 0. Increasing the prior mean accordingly would increase apparent replication success, so we suggest using several choices, ideally informed by existing replication efforts in similar domains. Hell's power analyses aid principled determination of which original studies are sufficiently informative on their own to be good candidates for replication. Interestingly, his analyses suggest that in the context of inherently implausible original findings, those with p-values above 0.01 are poor candidates for replication. Near that point, the sample size required for a well-powered replication study asymptotes to infinity. Other considerations are also relevant to replication success. One can assess the extent to which the original study is statistically consistent with the replication study, in that its data are compatible with the same underlying population parameter that is unbiasedly estimating the replications. And the authors who are commenting here have done some work on this one. This method assesses whether the replication and original studies point estimates are more distant than expected by chance, accounting for statistical uncertainty in both, and hence are conceptually different from Held's reverse Bayesian sensitivity analysis on the original study. I didn't quite get to the end, but I shall stop there. The last one is from John Ioannidis at Stanford University. Held proposes an ingenious method to assess the replication success for a replication study. The method builds nicely on analysis for credibility and more specifically on the concept of the skepticism limit. The proposed methods add a skeptical member in an already long list of commonly applied criteria in judging whether replication has been achieved. Table 1, which I'm afraid you can't see, shows how different the conclusions can be depending on how one judges replication in the Open Science Collaboration Project. The replication success criterion of Held is eventually as demanding as asking the replication study to have at least as large or larger effect size estimate compared with the original study, even though statistically significant original discoveries already tend to have inflated results. There is large variability of opinion about the extent and causes of the reproducibility crisis. Investigators whose findings are challenged as non-reproducible and those who have advocated for methods whose performance is severely challenged in the current reproducibility checks environment might espouse mostly the lower non-replication rate estimates. Many other investigators see much larger problems of non-reproducibility reflected in the accumulated evidence. The Held method may be more popular, mostly with the latter group. Nevertheless, different scientific fields may be represented and interpreted more accurately with different methods to count non-replication. For example, in fields that have inherently major biases in their measurements, design, conduct, reporting, and dissemination, for example, observational and nutritional epidemiology, even the Held estimates of success may be overestimates when interpreted at the skeptical p-value less than 0.05 threshold. PS, the skeptical p-value less than 0.005, or even much lower thresholds, for example 10 to the minus 6, may be appropriate in such settings. Conversely, for fields with rigorous designs, for example randomized experimental studies, and thorough preemptive avoidance of selective reporting through carefully adhered pre-registration, the Held estimate may be too pessimistic. I'll stop.
Right, thank you very much. So for the record, although we're not reading them out now, there have also been written contributions from Tim Freed and Christian Rover from Göttingen, Kuldeep Kumar from Bond University in Australia, Christine Chai from Microsoft Corporation in Redmond in the US, Alexander Lyon, Eric Jan, Vagamarcus from Amsterdam, and Louis Preachy from the University of Puerto Rico. And the reason for me reading those out is really just to emphasize the international reach that these papers have had. So before we call proceedings to a close, there's a firstly, I want to say, is there anybody else from the floor that would like, having heard those, to make a contribution? No? Okay, well, you've all got the chance to put something further in writing if you go away and think, gosh, there's something I wish I said. So you won't have very long, but you'll have a little bit of time to put it in writing. So what I'm going to do now is to call on the authors to reply, reminding them they will have an opportunity to do a more considered reply in the journal once they've had a chance to read all of the contributions in their written form. But if I can invite them up, so Ken first and then Leonhard to make any remarks that they'd like to make at the moment.
Thank you, and thank you to all the discussants. I'll keep this brief. I know people want to get to the pub and the quiz night, and who can blame them. Just a couple of quick things. The various comments about estimation and can't we do that as well? Yes, we can. It turns out, and you can see Rice 2010 for a way of doing that. Basically, a version that gets you wall tests, p-values as a Bayesian decision rule. Which is an ongoing area of research for me, and it does a whole bunch of other things, and it's very flexible as well, but different from the version, from the material that you saw presented today. There are various discussants, particularly the red ones there, who don't like testing at all, but as both Leo and I said, then we quoted David Spiegelhalter saying that testing is just, p-values are just too useful to ditch, and I think we both agree with that, and it's not going to go away, even if some people would like it to. Which is strongly relevant, but I want to come to Peter Deagle's point about 80% power. I believe, and there's a math stat thing, that if you have 80% power from two normal distributions under a null and alternative, if you take a 50-50 mixture of them, it's the threshold at which that becomes bimodal, I believe. So I'm not sure it's the most important thing you learned today, but it's another motivation for it. I'm sure there are many. Yeah.
Thank you for the comments and discussions. Yeah, so I feel challenged, like an original study result, right? So let's see if I can replicate it. No, to be serious, so I was pleased to learn from the proposer that this is an intuitive scientific metric for reproducibility. Well, that was really the aim of this work, that it's something easy to use for practitioners. Talking about the standards at EMA and FDA, that was something Jane Hutton mentioned. I think it's important to realize that the two-study paradigm that I mentioned is applied differently, usually. So in practice, what's happening actually at these drug companies is they run trials in parallel. So they don't do it sequentially. They just run it in parallel, right? And they are, both studies are, of course, well-designed and follow all the strict recommendations and by EMA and FDA. So this is not the scene or the setting I'm looking at, right? So I'm looking at really replication studies, like in psychology or the social sciences. Preclinical research is now a big field, and then it's different, right? So you have an original study where you question whether it is subject to bias, where you're not sure, and then you do a replication study and you wonder whether the replication study confirms the original study. So I think this is different from the at least phase 3 study design where the two-study paradigm is applied. Of course, you may have these issues that you mentioned, or that I mentioned, more in translation rather than replication, when you, for example, try to translate phase 2 study results to phase 3, then often you have issues that they don't translate as nice as you think they should. So medicine, of course, is its own field. I work in medicine. I'm a biostatistician. I'm aware of guidelines and of course, all the questionable research practices that are applied in medicine and then also in other fields. So, but that wasn't really the point of my talk. I was really aiming at a new method for the assessment of replication studies. Yes, Peter asked about calculating the power and that you have to fix the clinically relevant difference, which is, I agree, a bit strange, but I didn't have the time to go in more detail. It's easier in the setting of a replication study and because then you power the study to detect the observed effect estimate from the original study. Or you power it to detect half of it, as Sheila mentioned, right? So then, in a sense, you have a reasonable number that you just use. And so the figures I showed, they are powered to detect the same effect that we had in the original study, either incorporating the uncertainty or not. Okay, that was conditional and predictive power. If you power for half the size, then of course you get 4 times as much sample size. That's something I haven't looked at, but it would be interesting to compare this to the curves I showed you for replication success. So they will be closer to each other. And this is actually a common way. So in psychology, for example, in this replication project that I mentioned, in the replication effect estimates are on average half as large as the original effect estimates. So they use actually similar rule of thumbs to apply traditional sample size calculations. And what I did was to provide a new sample size calculation for this concept replication success. Very good comment about what's happening if the replication effect estimate is actually larger than the original one, which rarely happens in these projects, but it may happen. And so then actually, yeah, so the skeptical p-value will get smaller and smaller the larger the replication effect is. So this is really still, you know, measuring the conflict between the skeptical prior around 0 and the replication effect estimate. So that's something I would like to comment on further in the written contribution. Yes, and the comment by John Ioannidis, I agree that probably different thresholds have to be applied in different fields. I didn't discuss the choice of the threshold, really. That was just as arbitrary as the 5% level. And I just want to mention that the low rate of my proposal that he mentions was based on the 2-sided skeptical p-value. So if you would have done it one-sided, it would actually be slightly higher. And I think the one-sided approach is probably actually the thing to use in practice. Thank you.
Thank you very much. So if we could now thank both the speakers, the proposer, the seconder, and the discussants for a really fascinating meeting.